Hi everyone, how are you doing? I hope everyone's doing well. So before we begin, I want to ask if you have any question. What do you mean the code? Any question before we start? So the topic we're going to cover for this review is the first one will be flip-flops. Thank you, Sean. Thanks a lot. And the next one from that we will cover counter. And the next one from counters we will be able to build some arithmetic circuits which we can perform the multiplication and other kind of circuit. And let me know if you haven't covered some of these topics here. So the first one we will have a flip-flop and latches. And we know latches is basically two logic gate, which is two NOR, and have a feedback going back to one of the input and the other going back to this input, and this is SR, right? And then the truth table we will have if we input the 0, 0 here, and since we know the truth table for the NOR gate is output, let's say this output 0, 0, 0, 1, 1, 0, 1, 1. And so we know NOR is 1, 0, 0, 0, right? And what's going to determine the state here is whenever we have an input of 1. So let's start with 1, 0, which is this one here. And because we have an input S1 into this NOR gate, so that means we will have a 0 for sure at this output. And then going back to this other NOR gate here, we will have 0, 0, which is 1. So if this is Q and this is Q naught, then we will get this as 0, right? And then if we go back to 0, 1, then we will have Q as 1. And because this is the set state we have here, and we usually want the set state to be 1 and then Q to be 1. So this can be also written as Q and Q naught. And however, when we input both 1 into this circuit here, we are going to have some problem, which is undefined. This can be both are 0 and Q naught will be 0 as well. Zero, and we know 0, 0 is just storage, right? And let's see, so the next SR we will have a Nand gate. The truth table for this SR latch is shown here, which is going to be I can find it there. So let's start over. So 0, 0, 0, 1, 1, 0, and 1, 1. So for NAND gate, we have input here and then output here. 0, 0, 0, 1, 1, 0, 1, 1. And for NAND gate, we know this is 0 and this is 1. So we know that 0 is going to determine that the output will always be 1. So we use 0 first, and as we can already see here, if we both input 0 here, both of these will be 1, which means this is an undesired state. And if S is 0 and R is 1, and 0 going into the NAND gate here, we will have 1 at this output, and 1 going back to the NAND gate, 1, 1, which is 0 here. So then we will have 1 and 0. And for our next state, we will have 1 input here and 0 input for R. And then in this case, we can look at R first because 0 is going to determine the output. And in this case, we will have 1 here and 1, 1 going into this first NAND gate, and we will have 0 as our output here. And if both are 1, then this is our storage. Any questions so far? Okay, great. And we know that from SR is the most basic latch. And the definition for latch is it is level sensitive. Which means if we have an input here, like S or R here, and then we have the clock. We know that when clock is high, then our queue will start storing the value of S, depend on SR. So if our R is 0 and our S goes to 1 in this case, and then going back to 0, and this one goes back to 1. Let's take this as an example, and then we will get a queue of 1, 0, 1. And the definition for flip-flop is it is edge sensitive. And let's take the D flip-flop as an example. We have D latch, and this is our Q. And then we will go back to the D here, Q, and we have our clock here, and we invert this clock in order to get the edge sensitive. And we know this is our D flip-flop. Any questions so far? Okay, so for this one here, we can draw the timing diagram. Let's say this is our clock. And let's define our D flip-flop as a positive edge trigger. And then we have Q and Q naught here. And since we're looking at the positive edge of the clock, then we can draw a line down. And at this edge here, we know that the value of D is 0. So we know that Q stays at 0 and Q naught is 1. And then we can assume the same until the next clock cycle. And in this case, it is still 0 at this point for D. So for this timing diagram, it just keeps staying. For Q naught, it stays at 1. But if there is a positive edge here when it is the D is 1, then we will have Q going to 1 and Q naught will go to 0. So we will see that for D flip-flop, and clock trigger, Q, the next state of Q will equal to the value input into D. And from here, the next type of flip-flop we can have is JK. And the truth table for JK is as follows. Q, Q naught. And we know for 0, 0, this is just going to be equal to Q in the previous state, right? And this is Q naught. And when J is 0 and K is 1, this is reset. So we know Q will definitely be 0 and Q1 will be 1. And if J is 1 and K is 0, then this is set. So we have 1 and 0. And whenever both J and K are 1, it's going to be toggle. And by toggle, it means that the next state of Q will be Q0, and the Q0 will be Q. Any questions so far? And looking at this input when J equals to 1 and K equals to 1, because this is a toggle state, so then we can go back, go to our next type of flip-flop, which is T flip-flop, and Q. And let's say our initial state is Q, and the next state of Q is Q plus, which means next state of Q naught is Q plus naught. If we have a 0 here, and our initial state of Q is 0, then it's going to remain unchanged. So this will be 0, same as the previous state, and then this will be 1, which is also the same as previous Q naught. And if our Q initial Q is 1 and then our T is 1, and then we will see that Q plus the next state of Q is going to be the opposite, the invert of our previous state. So it's 0 and 1. And let's say we have 0 here and we have T as 1. So since our previous state is 0 and our T is 1, so that means it's going to toggle to the next state, and it's going to be 1 and 0. And if our T is 0 and our previous state is 1, and it's going to stay the same. And since that we know J and K are both 1, it's going to be a toggle state. So we can also make this T flip-flop as follow. So J and K. We can connect J and K together, and this will be our T input, and this here will be our clock, Q and Q naught. Any question? And now we can go to our counter. And for let's say we have 3-bit, just to keep it short. 3 bits counter. We know it's going to count from either count down or count up, and in this case, let's say count up. We'll have 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And let's say this is our output Q2, Q1, and Q0. And since we know that Q will change state whenever 1 occurs here, then we can make a really simple circuit, which is just a T flip-flop. And set it as 1 for our first one, which is Q0 in this case. And then if we look at this stage here, it's going to go to 0. I mean toggle whenever 1 occurs. So we can use another T flip-flop clock. And in this case, it's going to toggle whenever Q2 equals to 0, Q1 equals to 0, and Q0 equals to 1, right? For next state of Q1. So what we can build here is that T1 equals to Q2 invert, Q1 not, and Q0. And then the next time it toggles is at this point, which we will have Q2 invert, Q1, Q0. And going to our next toggle point, we will have Q2, Q1 not, and Q0. And since we know that when it reaches this point, we want it to go back to our 0, 0, 0. So at this point, this is a toggle point as well. Then we can write this expression as Q2, Q1, Q0. Any questions so far? And if we try to simplify the circuit, we can use a K-map to do so. So T1 K-map will be, let's say, Q2 and Q1 on top here. Okay, so the T1 on the table, we're looking at this one here, which is corresponding to the Q1 flip-flop. And so if we really want to make a table for this, then we will have T2, T1, and T0, right? And let's go back and look at T0. For our T0, this is our first flip-flop here. And then we will have the third flip-flop, which is Q2. This is our T2. And clock. So Q2, Q1, and Q0. And because we're using the T flip-flop, we want to check the point whenever it toggles, right? So if we want Q0 to go from 0 to 1, then we want T0 to be 1 in this state, right? And then since for Q0 it just keeps toggling, so for the 001 state going to 010 state, it's going to be 1 for T0 as well. And then we can fill out this table, which is going to be 1 for T0 at all times. And this is the reason why we input the 1 into the first flip-flop. And when looking at Q1, we want to see the point when it toggles. So we know from 000 to 001, Q1 state the same, right? So we want the T1 state to be 0, so it can stay at 0 when the clock ticks. But at this state here, 0 is going to 1. So we want T1 to be 1. So 0 can go to 1. And same thing for our 010 state. 1 is going to 1 for Q1, so we don't want it to toggle, so we want it to keep T1 to be 0. Does that make sense? And we keep doing the same thing to fill out the table. And looking at this state here, Q1 is going from 1 to 0, so we want it to be 1 at this state, so when the clock ticks, 1 will go to 0. So as we can see here, this just keep toggling like this, 0 and 1. Oh, sorry, did I write the equation wrong? Wait, did I? So our T1, the Boolean equation for T1, we can write it as Q2 naught, Q1 naught, and Q0, or it with Q2 naught, Q1, Q0, or Q2, Q1 naught, Q0, or the last one will be all 1. So this is just Q2, Q1, Q0. Does that make sense? And if we simplify this equation, we can use a K-map, Q2 and Q1, and then let's say our Q0 is at this location. And we have 0, 1. And we have and our first term is Q2 node, Q1 node, and Q0. So we have a 1 here. And Q2 node, Q1, and Q0, 1 here. This one we will have Q2, Q1 node, and Q0, which is 1, 0, this one here, with a 1 here. Last one will be this. And then we can simplify this by grouping this here. And we will get a really simple equation, which is T1 equals to Q0, right? And what's Q0? Q0 is our output of our first flip-flop here. So we can simply connect this to T1. Any questions so far? Okay, so how about T2? T2 is going to be 0 for the first state because it stays at 0 for Q2. And for the second state, we still have 0 because our next state here is Q2 is 0 as well. And then at this state, we have T2 to be 0 because we want to keep it at 0 for this state. And then at this 0, 1, 1 state here, we want Q2 to go to 1. So we want T2 to be 1 at this state. And then we follow the same method for the rest. So 0, 0, 0. And at this state, because it's going back to 0, 0, 0, and 1 is going to change from 1 to 0. And we can put the 1 here. Then we know our T2 will be Q2 node, Q1, and Q0, right? Or Q2, Q1, Q0. And then we can simplify this using the Boolean algebra, which we will get Q1, Q0, ended with Q2, invert, and Q2. And we know this is just a 1. So we will have Q1 and Q0. And to build this circuit here, we can use an Nand gate. Going to T2, right? And then before I draw the timing diagram for this, is there any question you have? And the clock, it's going to connect to the same source, which is the same clock. Did I answer your question? Uchi? And following this circuit here, counter circuit, you can draw the timing diagram. First, we will have Q0, Q1, and Q2 as our output. And then we have the clock. And let's say the T flip-flop is falling edge trigger. And then let's draw the clock pulse. And our initial state for Q0 is, for all output are 0, assuming that. And we want to look at the falling edge, so let's draw the line separating different cycle first. And we know that at Q0 we have a input T0 is connected to 1, right? So whenever the clock trigger, it will toggle. So 1. And for our Q2, we know the T input T1 is connected to Q0. So whenever the clock pulses, we want to look at the previous state. In this case, it is 0. And let's fill this out first. So when checking this clock cycle, we want to look at the previous state Q0 here, which is previously 0. So that means Q1 will remain unchanged, which is 0. And at this edge here, we know the previous value for Q0 is 1, and 1 is going into T1. So we know Q1 will toggle, and previously Q1 was 0, so the next state is 1. And then we follow the same thing for this one, which is Q0 is 0, 0 going into T1 and then clock pulse. And previous state for Q1 was 1, so it stays the same as 1. And then following this pattern, we can already see that it's going to be 0, 0, and this state it will trigger, so 1, 1. And then it will go back to 0 because this is 1 here. And going back to Q2, we know T2 is connected to Q1 ended with Q0. So we can already see that it's going to toggle only when Q0 and Q1 are 1. So we can already see before that the value are all 0. And at this point, because both are 1 for Q0 and Q1, and it's going to toggle, which is this is our 1. And then next time it toggles is at this location here. So we can just assume that the value will stay the same until that point. And then it's going to toggle back to 0. And after completing this, we can see the pattern is counting from 0, 0, 0 all the way up to 1, 1, 1, and then back to 0, 0, 0. Does that make sense? Okay, so for some reason my OBS is not. Okay, great, we're back. So this is our counter, and for counter it's easiest to use T flip-flop, which is just JK with J and K connected together. That's our T. Clock. And then now moving from the counter into the next one, we have sequential circuit, which is just finite state machine, I think. Oh no, we have the arithmetic. And for the counter, we can start building the multiplier, which we can have our adder here. And this is, say, A3, A2. Did your professor cover multiplier? Okay, so let's just, okay, not yet. Okay, then we can leave this for the last one, if you want to know how to make a multiplier. And now to the sequential logic. And assume that the problem is asking you to build a sequential from, let's say, 0, 0, 0, and then goes to 0, 1, 0, and go to 1, 0, 0, 1, 0, 1, and 1, 1, 1. Just for example. And we can see Q2. We're going to need a total of 3 flip-flops, right? And we basically follow the same step as we did before. And this is our, let's say we use a D flip-flop this time. So we have D2, D1, and D0. And for Q0, let's look at Q0 first. We know I see, okay. Shift register. Okay, so let's cover D flip-flop and then we can go to shift register. We know for whenever the clock ticks, next state of Q will equal to the input of D. So since at this state here, for Q0, 0 is going to 0, so we know our first stage for D0 will be 0, and then same for the second stage. And then for this stage, because 0 is going to 1, so we want this to be 1. And then it's going to go stay at 1 for this stage, so this one has to be 1 as well. And this stage is going back to, well, assuming it goes back to 0, 0, 0, then we will have to have an input of 0. So for D0, we can write it as Q2, Q1 not, Q0 not. And for D1, we will get, looking at the Q1 here, we will have 0 going to 1 at this stage, so we want this to be 1. And 1 is going to 0, so this will be 0 here. And then 0 go to 0, so 0 here. And then 0 going to 1 for this stage, so 1 here. And then this will be 0. So we can have the equation of and Q2, Q1 naught, and Q0. And for Q2, I mean D2. At the first stage, 0 is still going to 0, so we have 0 here again. And then second stage, we'll have 0 going to 1, so we want to have a 1 here. And then we need a 1 for this one because 1 is going to 1. And then this stage will have 1 as well. And then that stage we are going back to 0, so we have 0 here. So D2, then we will have Q2 naught, Q1, Q0 naught, or 2, Q0. And let's see if we can simplify this. So K-map. For our D0, we have 100. So 100 is this location here, and then 101. 101, which is this location here. So we can group these two together. So then this will equal to Q2, Q1 naught. And then for our D1, we have 000 and 101, which is this one here. And we cannot simplify this one. So we can only leave it the same. And for our D2, we have 010, so which is this one here, and 100, which is this one, and 101, which is that location there. And we can simplify this using K-map, and we get Q2, Q1 naught, or this one is 010, so Q2 naught, Q1, and Q0 naught. So we have three D flip-flop here. And let's say this is our first one, second one, and the third one. And D0 is the first one, D1, D2. So for our D0 input, we have Q2 ended with Q1 not. So we can draw an AND gate, and Q1 not is this one here. It's going to connect to this AND gate. And Q2 is going to be this one. And then we do the same for the other two. T1 we have the 3 input AND gate. And this is the OR gate, 2 input, and we have, let's go out of space. So we can simply connect this to Q2 not, Q1 not, and Q0 not. So this is our 3 input AND, and the next one we have Q2, Q1 not, and Q0, which is Q0 is this one, Q1 not is this wire here, and last one is Q2, which is this wire here. It's going to connect to this AND gate as well. So we basically do the same for D2. Do you want me to draw the timing diagram for this one? Okay, so let's draw a timing diagram. And okay. Say we have Q0, Q1, and Q2. We have clock here. And let's just assume it's falling edge again. And we know our Q0 is connected to, determined by the D0, which is equal to Q2 and Q1 not. Our D1 connected to Sorry about this. Okay, the darker one. Let me see if I can change this. It's not any better. Maybe if I let's see. Okay, this is better now. So Q0, Q1, Q2. We'll have clock here. Let me try to find. So D0 equal to Q2, Q1 not. If I remember this correctly, it should be Q2, Q1 not, and Q0. I think so. Yes. And for Q2, we have D2 equals to, it's Q2, Q1 not, and Q2 not, Q1, Q0. And we can start drawing our clock pulses. Oh, there's a ruler here. I think I can use this. So since it's falling edge, so we have to check each falling edge and separate each cycle. And let's draw the great. So let's just assume our initial state to be 0. And then when the clock pulse, we just check each D0, D1, and D2 to determine our next state of Q. So in this case, so since D0 is equal to Q2 and Q1 not, then we can already know that it's going to stay 0 because our previous state is 0, 0, 0. And 0 ended with 1 is still 0. So we draw this right here. And for our D1, we can already see that it's going to go to 1, right? Because 0, 0, 0 going into this one is going to output a 1. And then we can check the next state, which is Q2, Q1 not, and this is a 0 for sure. And Q2, this is also a 0, so it stays at 0. So we'll see 0, 1, 0. And when the next clock pulses, we can see Q0 is 0, and then for D0 we have Q2 ended with Q1 not. So this is going to stay at 0 as well. For our Q1, we will have 0, 1, 0, so D1 will be 0, right? And for our D2, we know this term here is going to output a 1 for 0, 1, 0, so we know it's going to 1. And after that, we can see Q2 is 1 and then Q1 is 0. And we know D1 will be, D0 will be 1. So Q0 will go to 1. And the other state we will have 0, 0, 1. I mean 1, 0, 0, so this is 1, 0, and 1, 0, 0, this one is 0 as well. And this one is 1, 0. So Q2 is 1 and Q1 is 0. So this term is going to output a 1. So this is going to be 1. This is going to be 0. And after this, so Q1 is still 0, so and Q2 is also 1, same as the previous state, so we know D0 will stay at 1. So our Q0 will be 1. And Q1 will be dependent on D1. So 1, 0, 1, which is going into this term here, it's going to output a 1. So we will have a 1 here. And for Q2, 1, 0, 1, this is going to stay at 1, right, because of this term. And then let's see if it goes back to 0. So we have 1, 1, 1, and we know D0 for sure will go back to 0. And for Q1, D1 is going to be, this term will output a 0. And this term will output a 0 as well, because 1, 0, 1. So this is 0. And Q2, 1, 1, 0, I mean 1, 1, 1, this will be 0, and then 1, 1, 1, this will be 0 as well. So it goes back to 0. And repeat the same cycle. So we will have a cycle of 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, and it goes back to 0, 0, 0. And then check with our previous requirement. We will see. So we wanted 0, 0, 0, 0, 1, 0. Let's cut this, compare it. So the previous problem, we are asked to build a sequential circuit of 0, 0, 0, 0, 1, 0, 1. This should be, oh, sorry. So this is Q2, Q2, Q1, Q0. So the order here should be, since our Q0 is on top, so this will be 0, and then Q2 is 1, so 1, 0, 0, 1, 0, 1, 1, 1, 1, and 0, 0, 0. So it's the same as our previous condition. And any questions so far? No question? Okay. Then let's go to our finite state machine. So for FSM, we can have milli and mole, right? And for milli, it is going to depend on both input and output. And for more, this is just going to depend on output. So if we're going to use our previous example to draw the state diagram, which is this part here. And let's say we want to output the 1 when we have consecutive, we have 2 consecutive ones. So we can start encoding our state. So let's say A will be 0, 0, 0, B as our 0, 0, 1, C as our 0, 1, 0, D as 0, 1, 1, E F is our 1, 1, 1. And let's say this is milli. So we know that A at this state, if we have an input of 1, our output will be 0, right? Because we need 2 consecutive ones. And so let's say our input is going to be we might not be able to use this example because we need to have an input value. And this is just a closed loop circuit here. So if we use a shift register, let's not use this example then. If we use a shift register, zero and 0, 0, 0. It's going to keep shifting, right? Depending on the input. And so our D flip-flop can be used for shift register. And in this case, we can use only 2 flip-flops because we can use our input. And this is our clock. Not input. And this is just going to some load. So if we only have 2 flip-flops, then we can say A equals to 0, 0, B equals to 0, 1, C equals to 1, 0, 1, 1. And then we can start drawing the state table. And this column will be our list of state. We have A, B, C, D. And we have our input here, which can be 0 or 1. And this will be our next state. And we will have our output here. X equals to 0 and x equals to 1 here. So we know that A start at 0, 0. So when x equals to 0, we know when the clock pulse is going to be 0 going into Q, and then the value of Q here is going to go to the Q here. So we know this is going to stay at A. And then when x is equal to 1, this is 1 here, and then initially our state was A, right? So 0, 0, then it's going to shift to the right. So we have 1, 0. And we define 1, 0 to be C, which is this one here. And we know our output will be both 0 because we need 2 consecutive 1. And then for our B, it's 0, 1. And then when we input the 0 into the circuit, and 0, 1. So then we will go back to A because it's going to shift right, so this will become 0, and this input here will go to this input here, so 0, 0. And then when it is 1, then we will have 1, 0, which will go into C, right? Because we have zero, 1 here, and then we input the 1, so this shift to the right. This will become a 1, and then this will be 0. So it's going to C. And for our output, when we have x equal to 0, we have 0 as well, right? Because it's essentially 0 and then going to the 0 and 1. So this is not going to define 2 consecutive 1. So 0 here. And same thing for the 1 as well. If we have a 1, the previous state the previous input here is 0. So we need to have 2 consecutive 1. So in this case, it's 0 as well. And now to our C. We have 1, 0, and if we input the 0 into the circuit, then it's going to shift to the right. So 0, 1 will be B. And if we input a 1, it will become 1, 1, so which is D. Now when we have an input of 0 and then at our C state, we have 0, 1, 0, and this 2 this is not two consecutive ones, so this is output as 0 as well. And if we have an input of x equals to 1, then we will have two consecutive 1, so this will be our output 1. And then for our D, if we input a 0 into the circuit in the clock pulse, and we will shift to the right, which is going to be B0, 1. And then 1 is going to stay at D. So then we will have 0, 1, 1 if x equals to 0. And this is not two consecutive, so we know this will be 0 as well. And x equal to 1, we'll have 1, 1, 1. And because we have two consecutive 1 here, so we can say this is going to have the output of 1. And to draw this state machine, we can start with A, and then going through the different input. So let's first start with x equal to 0. And we know x equal to 0 is going to go back to A. So input is 0 and output is 0 as well. And when x is 1, it's going to state C. But the output is still 0 when looking at the table here. And let's go to state C and then assume that we have an input of 0. With an input of 0, we can go to state B because it's what the tables show. And then our output will be 0 at this location. And when C is input 1, we can go to state D, which is one, and we will have an output of 1 here. So and let's go take a look at B. If we input a 0, then it's going to go back to A. With an output of 0. And if we input a 1, it's going to go back to C. And then now to our state D. State D we will have when input of 0 will go back to B. And with an output of 0 here. And when input of 1, then it's going to stay at D, which is going to be 1 with an output of 1. So now this is our unsimplified circuit, and in order to simplify the circuit, we can, simplify the state diagram. We can go back to the table here. Oh, wait, what happened? we know that A and B are the same, right? Because A, when input is 0, is going back to A, and then input 1 is going back to C. And we, with the output of both 0. And for B, it's the same as A. So then we can write out as B equals to A here. And then cross this one out. And then for our next one, we know that D is equal to C, because it also goes to BD, and then the output is the same as well. So we can cross this out and then say that C is equal to D. And take note that if for some reason the D output is 1 here, we cannot simplify this with C because their output is different. But in this case, we can do that because they have the same output. And we will have a new state machine here, which is this state. A and C for x equals to 0, x equals to 1, A, C. This is actually BD. D. And then output we have x equals to 0. Which is 0, 0, and 0, 1. And since we have BD here, and we already cancel out BD, the state of BD, so we know B is equal to A. Then we can just write this, replace the value for B, and then C is equal to D, so it's just AC. So we have a state diagram of A going back to A when we have input of 0 and output of 0. And then next we will go to C with an input of 1 and output of 0 because of the 0 here. And then from C we will get that it goes back to A when input is 0 and output is 0 at this location. And then for x is 1, we will have 1 with the output of 1. So we know that our state is state A is equal to 0, 0, and C is equal to 1, 0. And from this state diagram here, we can come up with a circuit that's going to look like this. Clock Q, Q naught. Q naught here. which is just our shift register, and this is our input X. Clock is connected to the same one. And then this will be our output according to the state diagram. That this will be connected to input, and this will be connected to the first flip-flop. And this is our output. But in this state here, we can have that our input X, A, C, and X, and this will be 0, 0, and 1, 0. So we know whenever X is going to this will be D and D, D1 and D0. Let's say AC. Whenever X is 1, X is 0, this will stay at A. And whenever X is equal to 1, it's going to go back to C, right? At this state here, so C is going to this portion. And this is actually our Q1 and Q0. And the next one will be whenever Q1 and Q0 are 0, 0 and X is 1, then A will go to C as well. So then we can draw a diagram. The Boolean equation D1 will be going from 0 to 1. D1 has to be X naught, and we know our A is equal to 0, 0. So let's say this is Q1, Q0 naught. So, but when Q1 and Q0 are 0 and our X is 1, this will actually go to this state, right? So that means X Sorry about that, I think I confused everyone. If we have Q1 and Q0 here, X equals 0 and X equal to 1. Let's say this is 0, 0, and 0, 0 is our state A. is our state C, 0, 1. So this will go back to 0, 0, right? Which is state A. And then for 1, it's going to go to C. C should be 1, 0. Okay, so x equals to, so this will be 1, 0. And then from C, if x is input at 0, then from this state diagram, it will go back to A. So 0, 0 here. And then it will stay at 1, 1, 0 when x is 1. So if we're using D flip-flop, D0, that means D1 has to be x ended with I see. Okay, so D1 will always be connected to x, and we don't even need a D2 in D0. Let me erase this. D0, because it's always going to be at 0, right? So this value here doesn't really matter. So D0 always equals to 0. It's not connected to anything. And then we have the simplified circuit here. It's going to be 1 D Q Q naught, clock here. And this is going to be 0 D Q. And since this one here is just going to connect to 0, it's never going to change. So we can discard this flip-flop here. And then this will be our input x and Q naught. It's going to come into clock, and this is Q naught. And we know we have to output a 1 whenever this is connected to, whenever we have 2 consecutive bits, right? Consecutive ones. So this is our output. And And comparing these two circuits, then we can see that the simplified state diagram will be simpler than this one. Sorry for the confusion. I got really confused myself as well. Is there anything I can clarify? Any question? And if no, then we can go see the multiplier circuit. So for multiplier circuit, we can use an adder. Say we have 2-bit. This is our carry in. And this is our output, which is output 0 and output using sum is better as 0 and as 1. And this is our carry out. And then right here we can connect a buffer. And buffer is basically a shift register, just 2-bit, so D, Q. And this is our S1 input here and S2. And this is our clock. And if we want to express, because 0, 0 to 1, 1, we have the range from 0 to 3, right? So for this 2-bit adder, we can perform the multiplication like 3 times, and this one here is dependent on the counter's bit. So if we have a 3-bit counter, and it's going to count from 0, 0, 0 to 1, 1, 1. And we have a total of, let's say, 0 to 7, right? So because for 7 we want to use it to stop the clock, and 0 from 6 we have a total of 7, clock cycle can use. So this circuit here, we can have 3 times 1 equals to 1, equals to 3, and then 3 times 2 equals to 6. Three times 3 equals to 9, and 3 times total of 7, 21. Okay, so let's say our B1 and B2 and B0 are going to be this input value defined by the user here, I1 and I0. And then this buffer here is going to connect back to the this is output 0 and output 1 back to our adder circuit. And this will be output as well. And then we have a counter here. Let's say this is a 3-bit counter. And this is going to have a clock going in. And for our buffer, we will have a clock as well. So C0 is basically the value passed into the buffer. Well, we don't really need to use that, but we can use that if we want. And this is just another C0 Q naught clock. And you can connect the clock here. And this will be our counter output, which is 3-bit, right? And it's going to be 0, 0, 0 to 1, 1, 1. And since we want our clock for this buffer to be stopped at 1, 1, 1, then we can start drawing the truth table. This is our output from counter. And the idea is that we want to have an AND gate here. And the clock is going into the AND gate. So if we set this maximum value set maximum. If we set it at 111, then the clock will stop at 111. So this one we want it to be 0, and the rest will be 1. So that means we can write this as our POS4, which is F equals to Q2, Q1, Q0, and for F we will get Q2, Q1, Q0, invert. So the 3 times 1 is saying that at this, whenever F is 1, it's going to enable the AND gate to pass the clock through the buffer, right? And then the buffer, whenever the clock ticks, the buffer is going to store the value S0, S1 into this O0 and O1, which is output, stands for output. So if we follow this logic here, then let's go back to the truth table here. S1 and S0. And O1, O0. And we know that S1 and S0 is based on I1 and I0, which is a user input. If I1 and I0 are 1 and 1, then we're basically passing the value to store into O1 and O0. And O1 and O0 is connected back to A1 and A0, right? So then B1, B0 is constant, and A1, A0 is dependent on O1 and O0. And initially we have O1 and O0 as 0, 0. And then when the clock pulses, then passing through the adder, we will have 1 and 1 here. And then 1, 1 will go to O1 and O0. And then this adder will become 1, 1 plus 1, 1, which is just 0, 0, 0, 1. 1, right? So this is basically 6. And we know 1, 1 equals 3. So 3 times 2 equals to 6, right? And let's say if we set our maximum value at 0, 0, 0, then the clock will never pulse the clock will never go into a buffer, which the buffer will never store value from S1 and S0. So our S1 and S0 will always stay at the same as I1 and I0. And let's say if our I1 and I0 is equal to 0, 1, this is just 1, right? And if we set our maximum value, if we set a counter to stop at, let's say 0, 1, 1, then we're going to go through these, and the rest will be 0. And whenever f is 0, it will disable the AND gate to prevent the clock from going to the buffer. So we have 3 cycles here. That means one will be able to have 3 cycles of addition. So 3 times 3, 1 times 3 will be 3. Does that make sense? Let me try to reopen another one so it doesn't lag so much. S0, S1. So this is going to go to the D flip-flop, Q and Q naught. It's going to go to another D flip-flop. Clock is counted to the same clock, which is going to be and then we have our counter here. Well, let's just use 2-bit counter to simplify this. And our output will be from 00 to 11. Depends on the user selection. This will be our clock, which is the same as this one here. And this one is going to require an AND gate. And we draw out the truth table for 0, 0, 0, 1, 1, 0, and 1. So Q1, Q0. And the output F here, we're going to based on the maximum value. If we want our maximum value for the counter to stop at, let's say, 1, 0, then we want F to be 0. This clock. To be able to block the clock going into the buffer. So the buffer doesn't keep storing value. So this is our I1 and I0 here. Carry out. So that means we can allow two of the states for F to be 1, right? And if we connect our Q to A0 and this Q to A1, then we will be able to do multiplication. And let's say let's say we want to do the multiplication of 1, 0. Let's say we want to do 2 times 2 times 2, which we want it to be 4, right? So that means our I1 and I0 has to be 1 and 0. And we have to set our maximum value for the counter to reach only 1, 0 and stop at 1, 0. So let's just assume the counter is going to, the internal circuit of the counter is going to allow us to set the maximum value. So in this case, we can set the maximum to be at 1, 0. So we can have 2 clock pulses pass through our buffer. And then let's draw the timing diagram. Let's say this is our feedback 1 and this is our feedback 0. And we have our clock here. And it's going to cycle through. This is our I1 and I0. And then we have the output of S1 and S0. So initially, if we set our I1 and I0 to be 1, 0 here, then we know that because S1 and S0, the adder is asynchronous from the clock. So let's set our clock cycle first. And we want to assume our initial value for our buffer start at 0 before the clock ticks. And therefore we can see that S1 and S0 equal to B1 plus A1 and B0 plus A0. And we know that A1 equals to F1 and A0 equal to F0. And by looking at this, we will see that initially we have S1 and S1 to be I1 and I0, right? So this is just 1 and 0 here. And then the clock pulse, then our S1 and S0 will go to our F1 and go store out in our F1 and F0. So we will get this part as 1 and this part as 0. 1 and 0 here. And then if we do this, then we will see that at this clock pulse, at this clock cycle here, F1 equals to A1 and F0 equals to A0. So it's going to be B1, which is equal to I1, which is equal to 1. 0, which is equal to 0. Then B1 plus F1 is equal to 1, 0, right? So B0 plus F0 equal to 0. So we will have this circuit here, so 1, 0, 0. And this will equal to 4. And because we only have S1 and S0 here, we should have another carry out, which is this part. And then this will become 1. And then S0 and S1 will go to 0. Does this make sense now? Okay, great. Sorry if this review is more confusing. I apologize. I will do better next time. Thank you for the support, Coleman. Is there anything else I can answer if you have any question? Okay, so for the timing analysis, I don't have knowledge about that, but I can go over it briefly and hope I don't confuse you. So we have Q here and we have a clock. And let's just assume this is a T flip-flop. And let's always assume our T stays at 1. And the clock will pause. Like this. And Q initially started at 0. So therefore, assuming it's falling edge again. So in the ideal situation, it's going to immediately go to 1. But in reality, it's not going to be that way. So we will have like a slight delay before it reaches 1 completely. And add this clock pulse here. It's going to have about the same delay. Here. And this is going to keep going. So we know there's a delay time at this location and this location. And for falling edge, and rising edge, trigger. We want the clock frequency to be, let's say the clock frequency is about 50 kilohertz. And what's our period? So the period is defined to be this time cycle here, right? So this is our T. And to get a period, we simply invert the frequency, which is 1 kilohertz. And it's going to be equal to it's going to be equal to 0.00002 second equals to T. And if our T, as long as our delay T here is less than 0.00002, the circuit will function properly, right? And let's see, if T is greater than 0.00002, greater than or equal to, it's going to be the circuit will not function properly because the delay here is larger than the period of the clock. And this one here, the falling edge already triggered, so it will become like the stable state, something like that. And then it's going to be something weird. So if assuming that our T is about 0.00118 something, then it will still have a 1 here, and then it's going to go back to 0 before it reaches the next clock pulse. So I would say that T, the period of the clock, has to be greater than the delay of the flip-flop from the input to output T, which is Q. Is this helpful? Or no? Okay, thank you. Okay, I cannot talk anymore. Is there any more question I can answer? Thank you, Nick. Thank you all for coming. I really appreciate it. And I apologize again for the confusion earlier. Any more questions? Okay. Sorry, I forgot to change the date. So, yeah, good luck on your exams. Thank you so much for coming, and have a good night. Yeah, I tried to turn off the camera so my laptop doesn't delay so much, but apparently it doesn't help at all. Thank you. Thank you, Uchi, and Coleman and Nick